Hi, I'm Ken Salisbury, and I'd like to share with you some of the devices that I and my students have developed. The first is a force reflecting hand controller, which is the equivalent of the haptic interface as we call them today. It had 6 degrees of freedom, 3 translation degrees of freedom, a telescoping axis on one of them, and then 3 rotational degrees of freedom at a gimbal where the user holds it. The counterbalance located at the base of it enabled the arm to be moved without having excessive torques in order to counterbalance the system. So it was naturally counterbalanced. This work was inspired by Tony Bejczy and his vision of having a robot controller, remote robot controller, that was kinematically different from the remote manipulator. And this technology was enabled in part by the increasing computational capability that enabled mapping between the master device and the remote manipulator. Jean Vertut was another inspiration. He was a researcher at the French Atomic Energy Commission. He had a real passion and understanding of using cables for designing very backdrivable, very smooth devices, such as needed in teleoperation. My own hand was a 3-finger device that was able to perform tip prehension motions. It was not designed for grasping, and thus there's no palm in it. It had 4 cables for each finger, and this enabled 3 combinations of tendon motions to control 3 of the 3 joints on the hand, and then a 4th combination of tendon tensions allowed the internal force in the system to be modulated so as to minimize the tension on the cables as needed. This was in part inspired by the work of Bernie Roth related to the kinematics and workspace of the hand, and in part by Victor Scheinman, who was known for developing the Puma robot. It was very sturdy and has been around for many years because of its durability. And I tried to incorporate that level of durability in my own hand. So the hand was double jointed so that it could be moved in anthropomorphic motions as well as arbitrary directions of motion so that it could perform some unusual types of grasping. It employed controlled stiffness, a subset of impedance, so that it could grasp an object with some robustness in terms of disturbances on the object that it was manipulating. And it could manipulate objects of various sizes. It could also grasp objects from the inside, which was novel. I don't know of other hands that can do that at this point. Another device, in this case developed by Bill Townsend, was again backdrivable using cable transmissions. He ultimately started a company called Barrett Technology, which commercialized the arm, and many of which have been used in laboratories for research as well as commercial applications. The arm employed cable transmissions in order to smoothly and with very low friction and good backdrivability to control the joints on the arm. We used impedance matching between the motor and the output link so as to maximize the power transfer into that link, which in turn maximized the acceleration of the arm. And with high acceleration and the work of Professor Slatin and Gunther Niemeyer, we were able to program the robot to track using 2 cameras on the ceiling, an object being thrown to it and to actually grasp it midair. I'm ready. Because the system was able to track the trajectory of the incoming ball, it was also able to accurately throw it back to the person who threw the ball. That same technology was licensed to Mako Surgical and was used as a programmable miter box effectively to guide a surgeon while cutting bone in order to give them a very accurate shape of the cut that was being made in the bone. More recently, this device has been converted to a system for rehabilitation where it's able to exert controllable forces to enable strengthening of stroke patients over time. The next development was the Phantom haptic interface designed by Thomas Massey. It was designed to exert a 3-degree of freedom force vector on the fingertip or a stylus. It was, again, cable-driven, very smooth, very back-drivable, able to give the sense of touching a virtual object, the shape, the compliance, the friction properties. And this device has been used by many researchers around the world. It has been commercialized by 3D Systems, and they've come up with a very nice embodiment on the right here, which has been used by researchers for all sorts of applications, including sculpting, psychophysics, medical simulation interaction, as well as more. We then developed a remote surgical device. Akhi Madhani was the designer of this device. Here it's using a haptic interface to control the motion of the remote arm. The remote arm pivots around the entry point of the patient through a kinematic mechanism. This technology was ultimately licensed to Intuitive Surgical and was one of the early patents that helped found the company. One of the parts of the design that I am particularly proud of was the handle that the surgeon holds on to, typically using a 3-degree of freedom gimbal for orienting the end point of the master would have singularities in it or bad points in the workspace. So by adding a 4th degree of freedom, thus having a 4-degree of freedom gimbal, we're able to use the internal motion or the homogeneous solution of the device to keep the handle away from singularities and away from the workspace limits. And this device has been used in millions of operations, surgeries around the world. We next developed the PR1 personal robot. This was developed over a period of 18 months by Keenan Weirebeck and Eric Berger, spending about $400,000 in donations. Keenan has since become the founder of Zipline, which has been a very successful company for delivering packages via flying drones. That device was used to demonstrate the mechanical capabilities of the system. This is teleoperated, but you can see that it's able to perform all sorts of operations, picking and arranging objects and moving them around. This was used as a fundraising video, and ultimately the system was picked up by Willow Garage and developed into a commercial version. Roughly 20 or 30 of these were built, 12 of which were given to researchers who competed for having the robot. Co-developed with this was the Roth operating system, which allowed researchers to collaborate and share results with each other. And this, the Roth system and the PR2s continue to be in use to this date. Here's a picture of the commercial version of it, which has become quite a platform for demonstrating quite controllable robots. One experiment that we performed at Stanford was programming the robot to get me a cup of coffee. It was able to navigate from my laboratory on the first floor through doors, avoiding people, using the elevator, ultimately to go up to the cafe on the 3rd floor and request from the barista a cup of coffee, which the robot was able to take and navigate back down through the elevator and avoiding people back to the laboratory. One interesting aspect of the operation was finding its way through the opening of a door that had a glass window in it. the vision system didn't work because of the reflections in the glass. So it had to feel its way by touching the glass gently and then sliding over to the left until it touched the handle and was able to grasp the handle to open the door. And finally, more recently, we've been developing simple third arm devices. These are passive with no motors, so they're inexpensive and very lightweight. In a sense, we're looking for the low-hanging fruit in the wearable robotics domain. We have developed a number of versions of it, including high-strength versions, as well as multiple arm connections. We've also developed a number of end effectors for it, including mirrors, magnifying glasses, wrist supports, and a number of different gripping devices, as well as a number of different belts for securing it to your body. There are a number of use cases for it, many of them including holding a tablet or interaction device relative to your body so that your hands are free to perform other operations. In the case on the left here, it's supporting a person with tremor or a weakened wrist. And then ultimately, one of the fantasies we've had in one of the future applications we believe for wearable robotics is to assist individuals in simple tasks, such as demonstrated here by a technician working on the bench, and through voice control, gaze tracking, or even more local autonomy, it was able to retrieve an object that the technician needed and deliver it to their work site. So thank you very much. It's been a pleasure to share with you, and I look forward to your questions.